Today, we're going to talk about relative dating, which is how scientists can kind of estimate the order of rock layers on in any given outcrop of rocks. So, we're going to talk about a few different rules with relative dating and what that means to scientists. So, we'll start out these notes with just an intro video to give you guys kind of a review on rock types and how scientists can estimate the ages of rock layers.
Hi guys, Squeaks and I are checking out our rock collections. Ooh, that's a nice one. Now, some people might wonder why we collect rocks. I mean, a rock's a rock, right? Well, you've probably noticed that rocks don't all look the same. Some of them have speckles or little bits of what look like glitter, and some of them are just one color. And rocks don't feel the same either. Some are coarse and gritty, and some are smooth. It turns out there are thousands of different rocks, so you could build a really big rock collection if you tried. But among all those thousands of rocks, scientists organize them into three main groups. These groups are called igneous, sedimentary, and metamorphic. And each group is based on how rock actually forms in nature. That's right, everything comes from somewhere. Even rocks. For example, igneous rocks form when magma, the liquid rock under the surface of the earth, hardens. You know about magma. It can erupt from volcanoes. Once magma comes above ground, it's called lava. And when this hot, melted rock cools and hardens, whether it's above ground, like on the side of a volcano, or deep underground, it becomes igneous rock. Now, sedimentary rock forms when other rocks break down. This happens a lot, actually, all the time, but it happens really slowly. Sedimentary rocks often form in water because they're made of pressed together parts from other rocks that were broken up and carried away by things like rivers and streams. As a river passes over the land, it wears down the rock beneath it into tiny broken pieces called sediment. Eventually, all that sediment settles to the bottom of the water and builds up. And over time, pressure pushes down on the sediment, squeezing the pieces together tighter and tighter until they form a new rock, a sedimentary rock. Finally, metamorphic rocks are rocks that have gone through a big change. Remember when we talked about caterpillars turning into butterflies? That process is called metamorphosis. And metamorphosis just means changing shape. And that's exactly what these metamorphic rocks have done. They change when they're exposed to things like really high heat or really intense pressure, or sometimes both. This usually happens deep within the earth, where rocks can get squished, bent, folded, but not melted. So those are the three main kinds of rocks. But how can you tell one from the other? It can be pretty hard, but sometimes we can find clues in the rock about how it formed, from how it looks or feels. So what do you guys think? Do you want to play Rock Detective? Okay, here's our first mystery rock. What kind do you think it is? You see those bendy stripes? This rock looks like it's been stretched and squeezed. It must have gone through quite a change. And in fact, intense heat and pressure gave this rock its squiggly bands. Because it went through a big change inside the earth, it must be a metamorphic rock. Now, what about this one, rock detectives? Check out those layers, kind of like a big cake. Those are layers of sediment that were put down by rivers and oceans over millions of years. Since you can see it's made up of smushed up layers of sediment, can you guess what it is? It must be a sedimentary rock. Okay, just one more. This stuff hardly looks like rock at all. Those big goopy loops of black rock look like they're practically melting. And at one time, they were. They were made when lava from a volcano spilled into the ocean and solidified into rock. And since this rock came from lava or magma, you know that's right, igneous rock. So now you know, there's more to rocks than meets the eye. They all have different colors and textures. Each one has a story to tell, a story of how it formed. So the next time you're out for a walk, keep your eyes open for the most interesting rocks and play Rock Detective on your own. And if you find a rock that you think is especially cool, send us a picture at kids@thescishow.com. We'd love to see them, and we'll see you next time.
Okay, so when we talk about relative age dating of rocks, we're talking about just comparing the ages of one layer, comparing it to another layer. When you're talking about things that are relative to each other, you're just comparing them. You're not giving actual numbers or actual times that these rock layers formed, but we're just going to kind of estimate the order that they formed. So when we're talking about relative ages of rock layers, we might be able to say this layer is older than this one, but maybe not this layer is 200 million years old. That would be called absolute age. That's not what we're talking about in this section. An example of relative age, I'm older than you, but I'm younger than Mr. Richards, right? That's not telling you exactly how old I am or exactly how old Mr. Richards is, but it's giving you the age order. Scientists can use different clues to figure out relative age. So where those rock layers are in the earth, that's a big, big clue. And like the shape of the rock, has it been faulted? Has it been folded? That kind of thing. Again, something that's bolded on this slide, that's something that's very, very important, is this does not tell the exact time or the exact age of this rock layer. This picture here that is inlaid in this slide, this is a screenshot from your book. They just want you to figure out the relative ages of these cell phones. So just by using clues from what you see on these phones, they just want you to put them in order 1, 2, and 3, which one is the oldest and which one is the youngest. I think it's pretty clear that the phone in the middle is the oldest phone. So that would be number 1. And then this woman here on the flip phone, that would be phone number 2. And then the guy in the bottom left with the Bluetooth would be phone number 3. That's the most recent. And without even realizing it, you're using clues to figure that out. First of all, the size of the phone, how convenient the features are, all of those things kind of play a factor into adding in clues of which one came first, second, and third. So scientists use what we call the law of superposition to date these rock layers, or to put them in order. We know, and they just talked about it in the video, that sedimentary rock forms in layers. So it's broken up pieces of other rock that come in, lay down, and then get cemented by water. And they form in layers. So there's, a layer that comes in, gets cemented, then a new layer of rock that gets cemented on top of that, then a new layer that gets cemented on top of that. So this gives us what we call strata, or layers of rock, where the oldest layer is on the bottom and the youngest layer is on the top. Now that's, of course, if those layers are undisturbed. That means if they haven't been folded, they haven't been faulted, no erosion, no significant erosion has happened. So if it's undisturbed, then the youngest rock is on the top, the oldest rock is down on the bottom. A good example of this would be like if you were to imagine a stack of newspapers. You get the newspaper delivered every day. If you throw the first one down on your table, and then the next day you put that day's newspaper down on top of the first one, then the next day you put that paper on top of the stack, and you keep stacking the newspapers on top, then you end up with the most recent newspaper on top and the oldest newspaper on bottom. Or excuse me, or a more realistic example in my world would be like a pile of laundry, right? Your oldest laundry is at the bottom of your hamper, and then the clothes you wore more recently would be closer to the top. This is a video. They'll just talk about superposition and stuff that I just explained.
Hi, it's Mr. Anderson, and today I'm going to be talking about the law of superposition. Law of superposition essentially says the older rock is normally going to be found on the bottom. And so right here we're looking at a section from the Grand Canyon, and you can see that all the rock above this line looks very similar. It's actually called Navajo sandstone. But if I go down to the next layer of rock, it's going to look the same, and the next layer of rock is going to look the same, and the next layer of rock is going to look similar. So horizontally, rock looks the same, but the law of superposition says the farther down you go, the older that rock is going to be. Another thing that you should understand is that rock is going to be laid down horizontally. In other words, rock rock will be laid down flat because gravity is always pulling down. Now, an example of where you might see this in your daily life might be in your locker. And so I grabbed a sample from a locker right here. So if I grab some of the stuff out, it looks just like that. We got a book and a notebook and some papers. The stuff that's laid down most recently, like this biology book, is going to be on the top, or like this looks like a geologic key. We might then have a notebook that was used fairly recently, but the farther I dig down, I find crossword puzzles and doodling, and way at the bottom, I might find like a blank sheet. Some sheet of blank paper, some headphones. Those are going to be found at the bottom. And so that means that those were laid down more distantly or in the past. And so the law of superposition is fairly simple, but the problems you can solve with it are fairly complex. And so this would be an example of a geology problem that you have to solve. And so we can see all these different rock layers. So the idea is to figure out, well, which one of these occurred most distantly and most recently. So could you put it in order from the thing that happened in the distant past to the thing that just happened a little bit ago? And so you might say some of these things might be easy, like probably this rock here, E, was laid down a long time ago, and this rock layer, F, was laid down fairly recently. But how do you do that? Well, you have to use the law of superposition and the law of horizontally laid down rock, and you can do pretty good at it. When I was thinking about how I could kind of explain this to you, the thing that made most sense for me was to use a drawing program. And so imagine I were to ask you this problem right here. I were to ask you, could you figure out all these rock layers, which one was laid down in the oldest, or which is the oldest and which is the youngest. And so some of this stuff would make sense, like this is probably older here and younger up here, but it's not always apparent until you actually see it take place. So let's take a look at what happened here. So this is me drawing it. I kind of sped up the drawing, and then let me pause it after a little bit. Okay. So let me pause it right here. So what happens? Well, we had this first layer of rock laid down, and then a second and a third and a fourth layer of rock was laid down. So we know that the oldest rock is going to be the rock at the bottom. But let's play what happens next. Oh, wow. Okay. So what happened there? Well, we had a fault. In other words, those rock layers, we'll say that look like this, were broken and lifted up. And when you're looking at problems like this, you try to match up the sides. And so you know that the rock was laid down before the fault occurred. And so we could say that this occurred before the actual break, because you couldn't have a break in this until it was actually laid down. Let's keep going again. So what happened next? Well, that whole rock layer was tilted. That's kind of hard to figure out how that might work. Oh, what's this? That's me using an eraser. Okay, so what happened next? Well, it looks like we had erosion taking place, and so there was rain and wind, and it washed a lot of that rock away. Can we tell that that occurred after the tilting? I think that'd be kind of a hard one. So let's keep going. What happens next then? Oh, it's a lava. Okay, so we had a lava flow, and then that lava eventually was eroded. And so this is horizontal now at this point. So we know that this occurred before or after we had all of this erosion and we had the tilting. Looks like some more rock layers are going to be added as well. So we're adding more rock layers. What happens next? Looks like we have a little bit more erosion taking place. And is that it? No, we have this. What is that? Okay, that is an intrusion. In other words, that's where molten rock is actually moving up. We call this a dike, and then that's causing this bulge, or like an intrusion, igneous intrusion, or rock that's actually intruding into other rock and then it's hardening inside it. And so when did that occur? Well, we can look on here and we know that it actually, since it's cutting across all of these and cutting across over here, it actually had to form after these rock layers formed. And so if you know a little bit about the law of superposition and the law of horizontally laid down rock, or horizontality, I think is what it's called, you should be able to put together some of the geology or how things laid down. Now, you normally don't see it like this unless you're actually taking a test. You usually see it something like this. And so what do you know using law of superposition? Let's take a look at this. This is a road cut. Usually you can't see geology because there's plants and stuff growing over it. But if you cut out a road or you cut out a trail or something like that, you can actually see the rock. And so here we have several layers of rock that were at one time laid down horizontally. And so we would say the oldest rock was down here and the youngest rock is up here. The whole thing was then tilted and then it was eroded. And so we have a unconformity here, which is going to be an area where it was eroded. And then we have new levels, layers of rock that are added on top of that. Since these are horizontally, we'd say this is the newest and this would be the oldest. So I hope that's helpful.
All right. So he was just talking about all of the different factors that go into the law of superposition. One thing I do want to make sure that you guys know is that the word superposition, that prefix super means on top or above. So that's your law that's saying rock layers form on top of one another. That's just a good clue to remember that. Like Superman can fly above everybody else. So superposition, that's where one layer forms above the next one. Okay, so in order to understand, here we go. In order to understand some of the things that he was talking about, you know, how the different layers might get disturbed, we need to talk about what that actually looks like. So first of all, he showed us at the very end tilted rock layers. So we know plate tectonics are very, very powerful. Sometimes they might break rocks. Sometimes they might tilt them. You might see folding happen. All of these are called disturbances. Tilting, again, which you see a picture of it right here. This is where your rock layers they'll start out forming horizontally. And then after they're formed, something happens that causes them to become tilted. Folding happens. You see it over here on the right-hand side. Again, these rock layers formed horizontally and then they got squished together, like at a convergent boundary. Faulting is just a break in the rock. It can either happen faulting downwards or faulting up on top. But again, the rock layers form first and then they get faulted. And then the last type of disturbance is an intrusion. An intrusion is an igneous rock that comes up from the bottom, because we know igneous rocks are formed from lava, or molten rock, which comes from inside the earth. So you might see an igneous intrusion coming up from the bottom. The layers have to be there first in order for the igneous rock to intrude into them. Sometimes you might have what's called an unconformity, which is just a missing rock layer. And this is what an unconformity might look like. It's where erosion has happened and we're not quite sure exactly like what occurred in between the tilting of these layers and then the laying down of these ones, because those rock layers have since been worn away. Unconformities can also happen like here if we have a lot of igneous rock or metamorphic rock that's exposed. Again, we're not exactly sure the exact order, but we can make some pretty strong inferences. This guy is going to talk about the law of original horizontality, which is, again, if you know what the word horizontal means, that means side to side like this. This talking about how rock layers first form this way, and then they can get disturbed.
I'm crouched amongst these beautiful banded rocks known as the Marble Bar. And one thing that might be the first thing for you to notice is that these bands are not horizontal, but they're inclined at quite a steep angle. And you can see that all of the bands all around in the background are inclined at that same steep angle. One of the things we'd really like to know is whether these rocks were originally sediments. And one feature of sedimentary rocks that we know from observing rocks and the processes that form rocks around us is that sediments tend to form horizontally in flat sheets. So for example, that's because of gravity. So for example, if I pick up a handful of sand and drop it on the ground, it's going to come to rest horizontally, not at an angle. So one thing we want to look for is evidence that these rocks were deposited horizontally originally, and if so, we'd like to know which direction is up, so whether these rocks originally faced up this way or faced up that way. So if these rocks were originally horizontal, they could have come to lay like this in one of two ways. They could either have tilted like this, or they could have tilted over like this.
All right. We're gonna skip past this video. This is just another video that shows more unconformities in rock layers. If you are interested in watching it, then it is linked in your notes. So now we're gonna talk about like how do we actually like put this puzzle together to put our rock layers in order. Again, we're talking about relative age, so we're just talking about comparing them to each other. So this rock is the oldest, or this layer is the oldest, or this event happened first, and then this is most recent. We don't need to get into actual ages. We don't need to put numbers to it, but we are just putting them in order. Okay, so first of all, the law of cross-cutting relationships. We already talked about superposition. Superposition tells us we know youngest layer is on the top, oldest layer is on the bottom. Cross-cutting relationships is talking about anything that cuts into your rock layers, like a fault or igneous rock that's coming up from the bottom. All this is saying is that the rock layers, the horizontal rock layers, have to be there first in order for something to cut through it. And the guy from the Bozeman Science video went over that too. Those rock layers had to be there first, and then they broke at a fault line, or the rock layers had to be there first, and then that igneous intrusion had to happen, cutting through it. So a fault or an intrusion has to be younger than the layers that it cuts through. That's one piece of the puzzle. Okay, so now we're going to put these rock layers in order just by seeing what we see and knowing the clues that we know. We know superposition, youngest on top, oldest on bottom. We now know cross-cutting relationships, stuff that cuts through rock has to be younger than the thing it's cutting through. So in order to put these rock layers in their correct order, I'm going to start with the oldest rock layer. My oldest rock layer is H. I know it's the oldest because it's on the bottom. On top of H, we had G, F, and then E. H, G, F, and E were all originally these nice horizontal layers. And then we had rock layer D form on top of that. Maybe, okay. We had rock layer D form on top of that. All of those layers were these nice horizontal straight layers. And then we had this igneous intrusion happen. So we had this igneous intrusion that ended up cutting up through the bottom of all of these layers. I know that the igneous intrusion happened next because that intrusion doesn't cut into the next layer, okay? In fact, there was probably some erosion that happened before C got laid down. After that igneous intrusion, then I had a fault, J. I know that J is younger than I because J cuts I. So J is cutting through I, which means I had to be there first in order for J, the fault line, to cut through it. After that, it gets pretty easy from there. We have some nice even rock layers, C, B, and then A sitting on top. Okay, let's move on to our next video.
There are three basic laws of relative rock dating. They are the law of superposition, the law of cross-cutting, and the law of inclusions. First, let's define what we mean by relative rock dating. Relative rock dating is where we determine the relative or comparative age of rocks to each other. This means that we know which is older and which is younger, but we don't know exactly how old they are. Determining an exact age of a rock is what's known as absolute or radiometric rock dating. We use relative rock dating laws to determine the relative ages of rock layers or features to each other. Again, we're only able to determine what is older and what is younger. Let's look at each of these three laws. The first is the law of superposition. The law of superposition states that in an undisturbed sequence of rocks, the oldest rocks are on the bottom and the youngest rocks are on top. We can compare this to an analogy of a laundry basket. Each day as you add dirty clothes to that laundry hamper, the layers stack one on top of the other. And as long as this stack is not disturbed, the oldest clothes will be on the bottom and the youngest will be on the top. The same is true with any undisturbed rock sequence. The oldest rocks are on the bottom and the youngest are on top. Let's now look at the law of cross-cutting. This law states that any feature that cuts across the sequence of rocks is younger than everything it cuts. Some of the features that cut across the rock sequence may be a fault or an igneous intrusion, either a dike or a batholith. And these features are younger than any part of the sequence they cut across. Let's compare the law of cross-cutting to tracks in snow or in sand. In this scenario, the older tracks will be covered by younger tracks. This allows us to determine the relative age of those tracks, where those that are on top or are not covered by anything are the youngest, and those that are covered by the most are the oldest. This is also true with any rock sequence with cross-cutting features. Those features are younger than all of the rocks they cut. Finally, let's look at the law of inclusions, or as it's also known, the law of included fragments. This law states that any rock or fragment that's included inside of another rock is older than the rock in which it's included. For example, if we look at this diagram, pieces of rock A are inside of rock B. This means that rock A is older and rock B is younger. This is because rock A had to be around first so that it could be included inside of rock B. An analogy that's similar to the law of inclusions is that of a fruitcake. A fruitcake includes a lot of chunks or other items, and those items or chunks had to be made and bought before they could be included in that cake. So what this means is that those chunks are older than the surrounding cake. The same is also true for rocks. Any rock that's included inside of another rock must be the older of the two. Again, we can use these relative rock dating laws to determine the relative or comparative age of rocks to each other. Again, this only means we can tell which is older and which is younger. We must use something else known as absolute or radiometric rock dating to determine specific ages for specific rocks. But these relative rock dating laws are very helpful in helping us determine the sequence of events that led to rock formation.
All right. I really like the way he used that law of inclusions analogy with the fruitcake. So sometimes you might see broken up bits of older rocks inside another layer. We know that those broken up bits had to come from a layer that already existed. So just like that fruitcake example, or you could think of like Jell-O that's got fruit in it or things like that. The chunks of fruit that are in that Jell-O had to be there before the Jell-O formed around it. So sometimes we can use fossils. This isn't just another thing that we'll talk about here. Sometimes we can use fossils to figure out relative age of rock layers based on what kinds of fossils we find in the rock layers. We know, and we've talked about this in 4.1, we only find fossils in sedimentary rock because sedimentary rock forms in a really gentle process in usually with water, which makes for a good environment for a fossil to form. If I find a fossil of an organism that I know lived a really, really, really long time ago, then I know that the layer I found it in is also from that really, really, really long time ago. It seems kind of like, well, duh. It's because it is. So this picture here, yes, it's a cartoon, but I think it does a really good job of showing, we have our, I guess that must be a cartoon alligator or maybe a crocodile. And that's on the top layer. And then the farther down inside these rock layers you go, the more ancient or the farther away from your typical alligator or crocodile we get. So the more fish-like and less reptile-like the organism, then I can guess it's probably an older rock layer if I know it's related to the modern reptiles that we have here. So based on the types of fossils that you find in your rock layer, scientists can kind of use that to also help estimate the ages and figure out relative age. Sometimes we'll find rock layers in order or in different parts of the earth that are not the complete picture. And this is what we call outcrops. Okay, so you might find an outcrop of rock over here that's got layers A, B, C, D, and E. And then you might find an outcrop over here that's on the, a couple miles away that's got C, D, E, F, and G. Well, I can use the information that I know, put those pieces of the puzzle together, and then I get a little bit more of a complete picture. This is what we call a geologic column. Geologic columns are like that perfect world example of, if I were to have all the information with all of the rock layers in all the correct order, this is the order that they would have formed in. So again, if I have, these, and outcrop number 1 over here, I have 1, 2, 3, 4 layers. And then I kind of see a little bit of overlap with this layer that's got like the little crescent shaped shells in it. And then I see this brick looking layer, a couple miles away in a different spot. I might be able to make some inferences. Okay, so yeah, they came in this order. I have this wood grain layer, this layer that's got pebbles, and then my brick layer, my layer with the shells, this gray one, and then the yellow one on top or tan. So again, geologic column is like you're in a perfect world, in your perfect sequence. What's the order of the rock layers? We know in real life, erosion happens, construction happens, all kinds of reasons why we might not get a full, complete picture of what all of the rock layers put together are. That's why it's important to get examples from lots of different places, lots of different outcrops. So this is just showing where do those outcrops come from, or where do they actually overlap here. That is the end of our 4.2 notes on relative dating. Next, you guys are going to do a couple of activities that deal with figuring out how to put those rock layers in order, as well as how to use some index fossils as well to figure out the relative ages of these rock layers.